Use the substitution method or the elimination method to solve the system. The system of equations that we have is y equals 4/7 x minus 5, and the equation negative 2x plus 21y equals negative 105. Now we're asked to solve this system with either the substitution method or the elimination method. And when you have the substitution method, your first step is to rewrite one of the equations by solving for a variable, either x equals or y equals. So I'm noticing that we already have one of our equations in that format with the y equals. The other method, the elimination method, you want to have all of your like terms lined up. So the system needs to look something like this. It doesn't have to look exactly like this, but most of the time this is what it would look like. And what you'll see here, I've got a mistake there, let me correct it. I put a plus here and that should be an equals. So what you should see is that your equation is lined up along the equal sign, and then all of your like terms are kind of stacked on top of each other, so that when you add the equations together for the elimination method, you're already lined up to combine the like terms together. And you can see that we do have the equal sign lined up here. However, our like terms, x, are on opposite sides. We do have the y's on the same side. So this system is not really set up right now for the elimination method. Now that doesn't mean that you can't use the elimination method, but there's some work to put in before you can start applying that method. So because of the way this system has been set up, I'm going to lean towards doing the substitution method because it's already ready for me to start that process. So I'm going to use that substitution method. I've already got y equals. So my next step is to take the expression on the other side of the equation, 4/7 x minus 5, and substitute that into y in the other equation. And that's going to give negative 12x plus 21 times 4/7 x minus 5 equals negative 105. I'm going to use the distributive property and distribute that 21 to both terms inside the parenthesis. That's going to give me negative 12x plus, well, when I multiply the 21, 7 goes into 21 3 times, and 3 times 4 is 12. So I have a 12x. And then 21 times 5 would be 105. That's a minus 105. So I've got an equation with only one variable in it. I'll start combining those variables together. Negative 12x plus 12x comes out to be 0. And now all of the variables have canceled out. And I end up with this statement, negative 105 equals negative 105. Now that statement is a true statement. So when you have a system where all of the variables end up canceling out, you know that you have a special case of the system. And because we ended up with a true statement, we know that this is the special case where these two lines, this equation and this equation, happen to be the same line. So they are the same line that are right on top of each other. I can show that if I take the second equation, negative 12x plus 21y equals negative 105. If I take that second equation and I solve for y, I'm going to add 12x on both sides. That's 21y equals 12x minus 105. And then I divide by 21 on both sides. That's going to give y equals, I would reduce that 12 over 21. Let's see, 3 goes into 12 4 times, 3 goes into 21 7 times. And if I divide negative 105 by 21, I'm going to get a negative 5. So you can see that that second equation, when we rewrote it in slope-intercept form, is actually the same as the first equation. So this is a system where we have two lines that are sitting right on top of each other. The solution to the system will be all of the ordered pairs that fall on top of that line. So it's not just one ordered pair that's the solution, it's all of the ordered pairs that are on that line. We would not include any ordered pairs that are not on the line, so we only want to include the ones on the line. So to say what the solution set is, we could write that in set builder notation. Set builder notation is where we write curly braces. We are going to state here what the solution looks like, or what the items in the set look like. The items in this set are all ordered pairs, and these ordered pairs need to specifically be on the line y equals 4/7 x minus 5. So the way that we read this is that we have a set of ordered pairs, and those ordered pairs must be on this line. Another way to write it is to write out an ordered pair, an x and a y, but we don't want to have two variables. So instead of writing the y, I know the y has to be 4/7 x minus 5. So ordered pairs of this form, x comma 4/7 x minus 5, will be ordered pairs that satisfy this system of equations. For this question, we want to use the properties of logarithms to expand the logarithmic expression. Wherever possible, evaluate the logarithmic expressions. So the expression that we would like to expand is log of square root x over 1000 y squared. And the properties that we're going to use for expanding this expression are the product rule, the quotient rule, and the power rule for logarithms. So specifically, the product rule and the quotient rule are the ones that we consider to be expanding. The product rule allows you to take an expression that is multiplied and turn it into the sum of two logarithms. And the quotient rule allows you to take a quotient or division inside the logarithm and turn it into the subtraction of two logarithms. What I like to do is I like to use these two properties at the same time, and in the expression that we have, look for factors in the numerator and factors in the denominator. The factors that are in the numerator will have logs that are positive, and a factor that comes from the denominator will have a subtraction or minus sign in front of it. So the expression that we have inside of our log is the square root of x over 1000 times y squared. So when I look at this, I can see I have a factor, just one factor in the numerator, and then 1000 and y squared are two factors in the denominator. So because of these product and quotient rules, each one of the factors will get its own logarithm. each factor from the numerator gets its own log, and each factor from the denominator gets its own log. So I'm going to be able to write this as log square root x minus log of 1,000 minus log of y squared. So you'll notice that this factor of square root of x was in the numerator, and the log has no sign in front of it, so we assume it to be positive. And we want it to be positive because it's coming from the numerator. However, these two factors, 1,000 and y squared, they were in the denominator, and so I have a negative on those logs. So those product and quotient rules have allowed us to expand that single logarithm into the log of each one of those factors. So this last property is a power rule, so it doesn't really expand into multiple logarithms, but if we have a power on an expression inside the logarithm, we can move that power to become the coefficient on the log. So we do have in this last term here, log of y squared, we have a power and exponent on that logarithm. So we're going to be able to use the power rule on that portion. But we also have on this first term here a radical. And radicals can be written as powers. This radical is a square root, and so we can write this as the 1/2 power. So we're going to write this as log of x to the 1/2 minus log of 1,000 minus log of y squared. And with those powers, a power of 2 and a power of 1/2, we're going to apply the power rule and write this as the coefficient 1/2 log of x minus log of 1,000 minus 2 log of y. And you'll notice one more thing that we can do in this sentence here. It says, wherever possible, evaluate the logarithmic expressions. This expression, log of 1,000, is log of a number rather than log of a variable. The log of the variable we're not able to simplify because we don't know the value of the variable, but log of a number we can simplify. We have log of 1,000, so we say, okay, I'm not sure what this log equals. Let me let it equal p for power. Log always equals the power or the exponent. Let me rewrite this in exponential form. So to rewrite it in exponential form, I need the base of the logarithm, which is usually written right here. And since nothing is written, I know this to be base 10. We have 10 to a power equals 1,000. 10 to what power is 1,000? We know that power to be 3. 10 to the third power is 3. So I'm going to be able to evaluate that logarithm and say that it equals 3. And that changes this expression to be 1/2 log x minus 3 minus 2 log of y. I probably should have had equal signs all along the way, but we've now expanded this logarithmic expression using the product and quotient rule and the power rule. In addition to that, we've evaluated expressions where we were taking the log of a number to get 1/2 log x minus 3 minus 2 log of y. For this question, we want to find all vertical asymptotes and create a rough sketch of the graph near each asymptote. We're given the function f of x equals 9 over x plus 4. When you're looking for vertical asymptotes, you want the function that you have to be in lowest terms. And that means writing the numerator in factored form, writing the denominator in factored form, and canceling out any common factors before you start solving. So we have a function that is completely factored in the numerator and completely factored in the denominator, and there are no common factors, so that's already done for us. And once that is written in lowest terms, you're going to take the denominator and set it equal to 0 and solve. So we have x plus 4 equals 0. I'm going to subtract 4 and we get x equals negative 4. So this tells us, by doing this process of setting the denominator equal to 0, we're finding where your function is undefined, because division by 0 is undefined. And that location is going to be the location of your vertical asymptote. Now that's true as long as you have written that function in lowest terms, because there's another type of spot where the function is undefined called a hole in the graph or a removable discontinuity. And those can happen if your function isn't in lowest terms. So we know that this is a vertical asymptote because that function was in lowest terms, was completely reduced. Now, we need to know the definition of a vertical asymptote to understand the next part of what we're doing. We're going to draw a rough sketch of the graph. And in order to draw the graph, we need to know what it means to have a vertical asymptote. So what it means is that as x approaches that value, the y will approach infinity or negative infinity. And you can approach this value of negative 4 from either side. You can have x approaching negative 4 from below negative 4, and y can approach infinity or negative infinity. And you can approach negative 4 from above negative 4, and y will approach infinity or negative infinity. So if we want to draw a sketch of the graph, we need to narrow down what's happening when your x is below negative 4 and when your x is above negative 4. So we need to narrow down what is happening with y. Is it approaching infinity or negative infinity on either side? So what I'm going to do is I'm going to think of negative 4 on the number line, and I want to choose a number that is just a little bit less than negative 4. And I also want to choose a number that is a little bit more than negative 4. So I'm going to choose negative 4.1 as a number that's a little bit less than negative 4, and negative 3.9 as a number that's a little bit bigger than negative 4. And this can be a little bit confusing because negatives kind of go the opposite way of positive numbers on the number line. So it might be helpful if you label the next numbers that are around it. The next number counting this way would be negative 5, and the next number going this way would be negative 3, and that can help make sure that you're picking the right numbers for being below and above. So I'm going to pick those numbers and substitute them into our function and see what happens. So if I substitute a negative 4.1 into our function, that would give 9 over x plus, not x. We need to plug in negative 4.1 for x. Negative 4.1 plus 4, and that gives 9 over negative 0.1, which is going to give you a negative number. So now I know that if I am below -4, my y value is going to approach -infinity. And then I need to do the same thing for being above -4. So I'm going to test -3.9, which is above -4. That's 9 over -3.9 plus 4. 9 over 0.1, that's a positive value. And so now I know that if my x is above -4, then my y will be approaching positive infinity. So now I'm going to be able to draw the sketch of what is happening near x equals -4. So I would have my coordinate plane, and I'm going to count over to -4. And at -4, we usually draw a dashed vertical line to indicate the location of that vertical asymptote at x equals -4. And then as we approach -4 from below, we're going to go to -infinity. So that means that my graph is going to be approaching -infinity when I'm to the left of -4, and my graph, my y values, will approach positive infinity when I am above -4. So this gives us a sketch of what's happening near that vertical asymptote at x equals -4. In this question, we want to solve the following logarithmic equation. Log base 3 of x plus 7 minus 3 equals negative log base 3 of x plus 13. So we've learned two methods for solving logarithmic equations. So I want to take a look at each one of them. One of the methods is to convert to an exponential. So when you convert to an exponential, you typically will have the log only on one side of the equation. And you use the definition of the log to convert it to an exponential equation. The base of the log becomes the base of the exponent. The log equals the exponent, and the exponential expression equals the value inside of the log. The other method that we've learned for solving log equations is a one-to-one property of logarithms, and some books call that the property of equality. And with this type, or using this method, you would typically have log base b on one side and log base b on the other side. So you would have a log with the same base on each side of the equation, and once you have that, because of this one-to-one property, you can say that what's inside the log on the left has to equal what's inside the log on the right. It allows you to eliminate the logs from the equation. As we look at the example that we have, you can see that this doesn't really fit into either of these. First, we notice that we have logs on both sides. However, this -3 doesn't, it kind of throws a wrench into it fitting this format where you have a single log on the left and a single log on the right. This extra term means it doesn't fit that format. It also doesn't fit this format because you have logs on both sides of the equation instead of having a log on just one side. So what that means is that we need to do a little bit of work before we are able to implement one of these methods. So what I'm going to do is I'm going to move this term that has a log in it to the other side of the equation so that they're on the same side. And so eventually we'll be able to use this method of converting to an exponential. So if I subtract log base 3 of x plus 7 on both sides. That's going to be a little bit messy, so I'm going to try something different. What I'm going to do is I'm going to add 3 to both sides. So I'm moving that term to the other side, and then I'm going to add this log onto the other side. So it will look like this. Log base 3 of x plus 7 equals 3 minus log base 3 of x plus 13. And now I'm going to add log base 3 of x plus 13 on both sides. And that gives log base 3 of x plus 7 plus log base 3 of x plus 13 equals 3. And now I have 2 logs on the same side, and I'm going to be able to condense these with the product rule for logarithms. So this becomes log base 3 of x plus 7 times x plus 13 equals 3. And now that I've condensed to have a single log on the left, I'm going to be able to rewrite this log equation as an exponential equation. So I'm going to use the base of the log. It's base 3. The log always equals the exponent. We have a power of 3. And then this exponential expression will equal the expression we have inside the log. That's x plus 7 times x plus 13. So now that we've converted this to an exponential expression, or equation, we're going to be able to solve it. 3 to the third power is 27. We're going to multiply x plus 3 times x plus 13. That's x squared plus 13x plus 7x plus, and I don't know in my head what 13 times 7 is. So we have 91, and that's 27 equals x squared plus 20x plus 91. I'm going to subtract 27 on both sides. That gives x equals x squared, 0 equals x squared plus 20x. If I do that subtraction, I need to borrow from the 9. And 11 minus 7 would be 4. So we have a plus 64. And I'm going to see if I can factor this. So let's try that, x and x. Let's see, factors of 64 are 1 and 64, 2 and 32. 3 doesn't go in there. About 4. 4 times 16. 4 and 16 can make a 20. So I've got a plus 4 and a plus 16. And I'm able to set each one of these factors equal to 0. And get x equals negative 4 and x equals negative 16. Now, logarithmic expressions have restricted domains. Log of a positive is defined, but log of a negative and log of 0 are undefined. So anytime we solve a logarithmic equation, we need to check to make sure that our answer fits into the domain of the logarithmic expressions that we have. So I'm going to check, and I'm going to zoom out here so we can see the original equation again. So I have that original equation written down right here. Actually, that might not be the original. Okay, so this is the original equation here. And I'm going to check to make sure that x equals -4 is in the domain of each one of these expressions. We have log base 3 of -4 plus 7 minus 3 equals negative log base 3 of -4 plus 13. So I'm focusing on what's inside the log. -4 plus 7 is a positive 3. -4 plus 13 is a positive 9. And so we're going to be able to keep that solution of -4. So then let's check the other one. X equals -16. That would give log base 3 of -16 plus 7 minus 3 equals negative log base 3 of -16 plus 13. And you can see that inside this expression here, -16 plus 7, that's going to give a negative number. Log of a negative is undefined, so we have to throw that solution of -16 away. So the only solution to this logarithmic equation is x equals -4. Right-cut riding lawnmowers obey the demand equation P equals -1/10 x plus 1,820. The cost of producing X lawnmowers is given by the function C of X equals 140x plus 7,000. We want to express the revenue as a function of X, express the profit as a function of X, and find what value of X maximizes the profit, and what is the maximum profit. In addition, we want to find the price that should be charged in order to maximize profit. So there are a couple formulas that we need to know in order to do this problem. So these are formulas that are used in business for revenue, and the formula for revenue is R equals X times P, where X is the number of units and P is the price. We also need to know a formula for profit. And profit is revenue minus cost. So we need to do part A before we're able to do part B. So we're going to start with part A by expressing revenue as a function of cost. So we have that formula. Revenue is X times P, and we were given this demand equation, which this P in the demand equation is the same P that is in this revenue formula, the P for price, the cost of producing X lawnmowers. Oh, sorry, that's not right. That's a cost for later. But in that demand equation, that P stands for price. So we're going to be able to use that price in this formula. So we have X times -1/10 X plus 1,820. And we'll distribute that X to each term and get -1/10 X squared plus 1,820X. So now we've answered part A. We've expressed the revenue as a function of X. And what that means is that the variable within the equation is X. Up here, when we just have the formula, we have two variables, X and P. So we want just one. And then in part B, we want to express the profit as a function of X. And I gave you that formula. Profit is revenue minus cost. We just constructed that revenue function, so we're going to substitute that in for R. And the cost function was given to us, and we'll be able to substitute that into this portion of the formula. So we have revenue -1/10 X squared plus 1,820x minus cost, and I'm going to put parentheses after the minus so that we make sure that we're subtracting the whole cost function. That's 140x plus 7,000. I'll distribute that negative, that minus. That will give negative 1/10 x squared plus 1,820x minus 140x minus 7,000. I'm able to combine these like terms to get negative 1/10 x squared. And let me do that math. 1,820 minus 140, so I need to borrow. Borrow from here. 12 minus 4 would be 8. 7 minus 1 is 6. Okay, so we have plus 1,680x minus 7,000. So now we've answered part B, which was to find the profit as a function of x. Once again, that means that the only variable is x in the profit function. So then on the next part, we want to write the value of x that maximizes the profit. So there's been a little bit of theory to develop the explanation of how we get the answer for this. What we need to notice is that our profit function is not just any profit function, it happens to be a quadratic function. And we know about the graphs of quadratic functions. The graph of quadratic functions are parabolas. And we know what a parabola looks like. We also know that if we know the leading coefficient of that quadratic, it will tell us whether that parabola is facing up or down. And the fact that this leading coefficient is negative tells us that our parabola will be a down-facing parabola. And that's significant because of what we're trying to do in this problem. In this problem, we're trying to maximize profit, and the fact that this parabola is facing down shows me that the maximum, the largest y value is going to occur at that point, which is specifically the vertex of the parabola. And we do have some formulas that we can use to find the vertex. The vertex of a parabola will be the ordered pair HK, and we have a formula for H. That formula is H equals negative B over 2A. So we're going to be able to find the value of x that maximizes the profit by finding the vertex of that quadratic. So for our quadratic, we have that profit function, P of x equals negative 1/10 x squared plus 1,680x minus 7,000. The value of a is the coefficient of the squared term, negative 1/10. The value of b is the coefficient of the x term, 1,680, and c is that constant, negative 7,000. So if I want to find the x coordinate of the vertex, I'm going to do negative 1,680 divided by negative 1/10. Negative and negative become a positive. I'm also going to multiply by the reciprocal. So that's 1,680 times 10, which is 16,800. So the maximum profit will occur when we sell 16,800 units. I'm going to zoom out a little bit because I'm running out of space. There's a second part of this question that is asking to find the maximum profit. So I'm going to substitute that into the profit function. So if I calculate profit at 16,800, that's going to give me the maximum profit. So it's negative 1/10 times 16,800 squared plus 1,680 times 16,800 minus 7,000. I think it might be worth it to bring my calculator in for this calculation. Okay, so I got so caught up in dividing by a fraction that I didn't use the vertex formula properly, so let me make that correction. So I'm going to point out where my mistake is before I do any erasing, so in case you were following along, you can make the same correction. So in the vertex formula, we want to do negative b over 2 times a, and you can see here that I only divided by a and not 2 times a. So I need to make that correction. So I'm going to erase what I have here, and we're going to make that 2 times negative 1/10. And so that's going to come out to be negative 1,680 over, let's see, that would reduce 2 times negative 1/10 would reduce down to being negative 1/5. A negative divided by a negative would be a positive, and we would multiply by the reciprocal, so that would be 1,680 times 5. So I'm going to get my calculator to do that. So we've got 1,680 times 5 would give 8,400. And I'm much happier about that number. 16,800 seemed very, very large. So let's change that 16,800 to 8,400. And so we are going to type in, we're substituting 8,400 into the profit function. That's negative 1/10 times 8,400 squared plus 1,680 times 8,400 minus 7,000. So that gives us a profit of, it looks like 7,049,000. So that answers both parts, both questions in part C. So in part C it says find the value of x that maximizes the profit and what is the maximum profit. So we're going to get a maximum profit of 7,049,000 by selling 8,400 units of our lawnmowers. So we have one more part to go, and we want to find the price that should be charged in order to maximize profit. We've done a lot of work, so you may have forgotten, but we were given an equation called the demand equation, which gives us the price based on the number of units sold. So part D can be answered by substituting 8,400 into the demand equation. That's -1/10 times 8,400 plus 1,820. So multiplying 8,400 by 1/10 will cancel out one of those zeros, so we get -840 plus 1,820. So let me do that subtraction. I need to borrow again. So I get 80, and I need to borrow again. 17 minus 9 would be 9. So we have 980 is the price that we should set for the lawnmowers. We should charge $980 for those lawnmowers. On this question, we want to find the equation of all horizontal asymptotes, if any, of the rational function. And this rational function is f of x equals 7x cubed minus 9x squared plus 2 over x squared plus 6. Now, the actual calculation of horizontal asymptotes involves calculus. And since we're in an algebra class, we're not going to be doing the calculation. The rules around finding the horizontal asymptotes can be summarized. I've stated some rules here. So what someone has done is they've gone and used the calculus in certain situations and have been able to narrow the answer down to a certain set of circumstances. So in our algebra class, what we do is we memorize the conditions of each one of those circumstances, and then we're going to be able to determine what the horizontal asymptote is based on those circumstances. Now, these summary of rules are based on the degree of the denominator and the degree of the numerator. So we need to know the highest power on the variable from the numerator and denominator. So the degree of the numerator is going to be n, which is the highest power on x from the numerator, and the degree of the denominator is m, which is the highest power on x from the denominator. And all of the rules are based on comparing those values of the degrees. So in this first one here, it says if the degree of the numerator is less than the degree of the denominator, then we're going to have a horizontal asymptote of y equals 0. If the degrees are equal to each other, then we're able to find the horizontal asymptote by doing the ratio of the leading coefficients. So let me highlight those leading coefficients, a sub n and b sub m. The ratio meaning we divide those leading coefficients. And then you have some other cases where there is no horizontal asymptote. So in both of these cases, n is equal to 1 more than m. The degree of the denominator is 1 more. I think I said that wrong. The degree of the numerator is 1 more than the degree of the denominator. Or in this last case, the degree of the numerator is a lot more, 2 or more, than the degree of the denominator. So we have no horizontal asymptote here, and no horizontal asymptote here. So we need to figure out the degree of the numerator and the degree of the denominator, compare them, and decide which case we're in. So looking at the numerator, I can see that the highest power on x is 3, so n is equal to 3. And from the denominator, the highest power of x is 2, so the degree of the denominator is 2. So if we look at these, we can definitely rule out case 2 because they're not equal to each other. And if we compare 3 and 2, 3 is more than 2, so we can rule out that case. And then we can see this one, it matches. 3 is 2 plus 1. The degree of the numerator is 1 more than the degree of the denominator. So in this case, we have no horizontal asymptote. There is a different type of asymptote called an oblique asymptote, but this question is not asking about that. It's only asking about horizontal asymptotes. So we're going to say that there is no horizontal asymptote for this function. Now, if you're interested, you can find this other type of asymptote, the oblique asymptote, using long division. So let me zoom out for a second just to give you an idea of how this process would go. You would take your denominator and divide it into the numerator. And this is long division. I would think, what can I multiply by x squared to get 7x cubed? That's a 7x. Then I'm going to multiply that 7x by both of the terms on the left. 7x times x squared would be 7x cubed. 7x times 6 would be a plus 42x. And then with long division, you change your signs here. And that's going to cancel out these first terms. And you're going to carry down the 9x squared, the minus 42x, and the plus 2. You repeat that process over again. You're trying to match x squared with 9x squared, negative 9x squared, so that's a negative 9. Negative 9 times x squared is negative 9x squared. Negative 9 times 6 is a negative 54. You're going to subtract, changing these signs. We'll cancel out that first term, and you carry down the negative 42x, and 54 plus 2 would be 56. And now, because this power is lower than this power, we're now at a stopping point. And what you see up here is going to be the oblique asymptote. Y equals 7x minus 9 is the oblique asymptote for that rational function. Thank you for checking out my videos. Have a great day.